epsilon. That's wrong. Okay, that's the wrong formula for the stored energy in the material medium. This should be the correct formula. Okay, are there any questions? Yes?
Where do you use the fact that omega double prime is much less than omega prime?
Where do I use the fact?
Yeah, that omega double prime is much less.
Oh, I use the fact here. This definition is for time harmonic signal. This has meaning of the fact that the real part of this is the time average of this. This is a time harmonic oscillator concept. So if I don't use that fact, I cannot say that this is some kind of a power flow. Okay, I make omega double prime extremely small so that this still has the meaning of power flow. And then if I look at this thing, it should be conserving energy in this fashion. And this implies that W must be that quantity over there, and hence I get this extra formula.
What happens is if omega double prime is comparable to omega prime, then what happens?
Then this proof does not go through.
So, which means that we can't consider that to be power flow, right?
We can't consider that to be a power flow. What it says is that omega double prime can be extremely small, and this proof will be valid. So it should be valid in the limiting case of a time harmonic signal. If omega double prime tends to 0, this should be the energy density stored in the material medium. Not changing mu to mu, not changing mu not to mu or epsilon not to epsilon, which is sometimes written up in some textbook. Okay. So any questions on this? Any more questions? Yes.
So the reason to do the Taylor theory expansion for time and height is also assuming material frequency distance.
Oh yeah. If the material is not frequency dispersive, then this term will not exist. But as I said before, the fact that this term is there and this term is there, okay, is because of material. Material gives rise to polarization. And they are all molecular or atomic effects. And those atoms have finite masses according to Newton's law. You cannot move those things immediately, they have inertia. You cannot polarize a molecule immediately or instantaneously. So you will have frequency dispersion for this material thing. And because of frequency dispersion, it gives rise to different energy storage. Okay. Any more questions regarding this? Okay, no questions. Very good. Okay, let's go and do something else then. So let's look at the vector wave equation. Vector wave equation for an isotropic medium. Okay. And for an isotropic medium, if you assume that there are magnetic current in a system, then the vector wave equation will look something like this. And as we said before, we actually don't have to solve the third and the fourth equation. We can work with this equation. Then we can go to time harmonic signal. Then we will have this kind of equation. And this M is a magnetic current. Okay, this M is a fictitious magnetic current. Okay, how do you make magnetic current? You can use current loop antenna, right? If you have a current loop antenna, it is like a magnetic dipole, because the magnetic field that it produces is like that. Okay. So as we said before, everything is embodied in these two equations. Actually, we can reduce these two first-order differential equations into one second-order differential equation. So the way we do that is to multiply this equation by mu inverse, and then take its curl again. So if we do that, then we will have curl of mu inverse curl of E is equal to, if you take the mu inverse of this, I will have curl of H minus curl of mu inverse of N. Okay, then I can use the fact that curl of H is equal to that to simplify the second term. So I get omega squared curl of H is equal to epsilon dot E plus I omega j minus curl of mu inverse dot N. So I have this equation . And this is now a second order partial differential equation. And only one equation is concerned. Okay, no more the second equation, because the second equation has been absorbed into the first equation. And by the same token, we can eliminate the E field and obtain a very similar equation. But we can also use duality principle to write down the second equation right away. And by duality principle, duality principle uses the symmetry of Maxwell's equation that says that Maxwell's equations look extremely symmetrical. Okay, if you look at this equation, if you replace E with minus H, H with E, and then you replace M with minus J, and so on, the first equation becomes the second equation. Or another way to look at it is that you replace E with H, H with E, E with minus epsilon, epsilon with minus mu, you will get that too, and then M with minus J, J with minus M, you will get the second equation. So you can get these two equations to flip-flop by just changing the quantities or do a mathematical mapping. So once you have obtained a set of equations using some manipulation, you can say that I change mu to minus epsilon, epsilon to minus mu, and then J to minus N, M to minus J, and so on, and obtain the second equation very easily. The second equation must be of this form. Okay. So you can get the second equation by just changing E to H, H to E, and then mu to minus epsilon, epsilon to minus mu, n to minus J, J to minus n. You get the second equation because of the symmetry that these two equations have. Okay, so we don't have to derive the second set of equations usually. We can just invoke duality principle. But we need only to solve one of these two equations. They are sufficient because we have converted one of them, two first order PDEs into one second order PDE. Okay. So if you do any computation, you either have to do the computation with this one alone or that one alone. That should be sufficient. So everything we need to know about electromagnetic theory should be derivable from either this equation or that equation. All the things that you have learned about Maxwell's equations should be derivable from just this equation alone. So like things like duality principle, reciprocity principle, boundary conditions, and all those things should be derivable from just one of them. So in undergraduate courses, we always look at the 4 Maxwell's equations and want to derive all our boundary conditions from them. But what I'm claiming is that this equation alone has it embedded all the boundary conditions that we need to solve any problems with. So let's prove that we can derive all the boundary conditions that we need from this equation alone. Okay? So let's take this equation and have a boundary between 2 media, mu1 epsilon 1, mu2 epsilon 2. Okay, you have a media interface, and let's see what kind of boundary conditions we can derive. Okay, this media interface might have embedded in it some surface current, Js, Ms. Okay, and let's perform an integration of this equation on a small loop in this manner. And let's call it small loop having a contour of C. So if I perform a curve over this small loop, the curve becomes a line contour integral over C. Okay, becomes the contour integral. No, it should be the other way around. If this has an area A, okay, by Stokes theorem, this should be true. Okay, this is just Stokes theorem. Okay, so I invoke Stokes theorem and integrate this first term, second term, and third term over that cross-sectional area. The first term can be simplified by Stokes theorem, and then the first term becomes just dl dot mu inverse dot curl of E. The first term just becomes that. Okay. The second term will still involve the integration over A, so it will just become minus omega squared ds dot epsilon dot E over the cross-sectional area. And then the right-hand side would have I omega ds dot j over the cross-sectional area that I'm integrating over. Okay? And then I have the last term that I can invoke Stokes theorem again. Stokes theorem makes it into a line contour integral over C dot mu inverse dot m. Okay? I invoke Stokes theorem and get the last integral. So the first integral and the last integral becomes line integral. And this last integral is equal to 0. This last integral is equal to 0. Why? Why is that equal to 0? Because any currents that I have in this system are surface currents. Okay, I have surface currents. This current will only reside on this surface. But my line integral is over this thing. Okay, so this line integral and this current sheet never coincide. Even if you operate with the mu inverse just change the direction of that current, but does not bring it out of this surface. Okay? And hence this is always equal to 0. I think somebody asked me this question before. Why this is 0? This is the reason why this is 0. Okay? And then we're only left with the first and the second term and the third term. But this thing becomes very, very small in the limit when we shrink this thing into a tiny loop. We make it very, very tiny. This cross-sectional area becomes very small, and this will go to 0. And if there's a current sheet, okay, this would only have a contribution from the current sheet. So if I go through the proper adjustment to this, then this first term is just the line integral from here minus the line integral from here. Okay, this integral plus this integral. The integration over here is very, very small. Okay, so the first term I can rewrite as being equal to dl mu inverse dot curl of E1. Okay. From A to B, I can call this A to B. Okay, the section. It could be A to B. Okay, it can be A to B on this side. Okay, and then minus the other integration, dl A to B with the negative sign because it goes in the opposite direction. Mu inverse dot curl of E2. Okay, and then the second, this term is 0, and this term only has the current sheet contribution, and it can be written as I omega dl n cross L dot Js. Okay, so I can define an n that points in this direction, and L that points in that direction. L cross N will give me something that comes out of the blackboard or into the blackboard, and that gives me the current sheet that is flowing in the thing. Okay, I can write the current sheet contribution as this, and then if I work things out properly and let the thing shrink to 0, then what I have is that I will have L dot mu inverse dot curl of E1 minus L hat dot mu inverse dot curl of E2, okay, is equal to I omega n cross L dot of Js. Okay, this one is just the H field. This is proportional to the H field, this is proportional to the H field. And finally, I arrive at the boundary condition that n cross H1 minus H2 equal to J sub s. Okay, the other kind of boundary condition that you can derive directly from Maxwell's equation. It's just a proof that all the boundary conditions that we have needed for Maxwell's equations are embedded in this equation. You can derive this tangential H is equal to continuous boundary condition from that equation as well. And you can also derive, as shown in the textbook, that tangential E is continuous except for the current sheet. You can also derive this boundary conditions from this equation. The important thing I want to emphasize is that solving this equation alone is enough because it has also embedded in it all the boundary conditions that we need to solve Maxwell's equation. Yes?
The second equation should be a plus sign after the
Here?
yeah.
Let me see what I wrote down. I wrote down,
Because if you are swapping
Oh, yeah.
J,
I have a plus sign in my thing. Okay, you swap J with minus M, N with minus J, U with upon. Yeah, it has a plus sign. Okay. So what is important is that when you do computational electromagnetics, you always wonder where the boundary conditions have gone. How come we don't worry about them? Mu is inhomogeneous, epsilon is inhomogeneous. All the boundary conditions that you need are in this equation itself. If you solve this equation correctly, the solution will come up correctly to obey all the boundary conditions that you need. Tangential E is continuous due to the magnetic current sheet, tangential H is discontinuous due to the electric current sheet. Okay? So we stop here, and on Thursday, I won't be here, I will have Michael Chow come and lecture, and he will lecture starting at 9 a.m. Okay? And then next Tuesday, I won't be here, so we'll cancel the class for next Tuesday because I only owe you half an hour left, right? Because I lecture half an hour more this time. My teacher is going to lecture half an hour more on Thursday. And when they come back next Thursday, I will lecture half an hour more. So I'll catch up with you in terms of what I owe you. Okay?